Hello, welcome. Today we're going to review sex-linked trait Punnett squares and go over the answer key for that. And then after that, we are going to go ahead and go over how to fill these out in pedigrees. All right, so part one, determining sex determination in humans, or diagramming sex determination in humans. What is the genotype of the female parent with respect to gender? So females, we always go with XX. And so we're going to put one X in each of these. Remember, these represent the possible eggs. We're just passing on the X chromosome here, so it's got to be an X chromosome in it regardless. What's the genotype of the male parent? And actually, these are the chromosomes, so it'd be XY. So we put an X in this box to represent one possible sperm cell, and here's the other possible sperm cell. So what is the probability that the first child that the couple have will be male? So we got to fill this out. So we take an X from there, XX female. XX female, and here we're going to have an X and a Y, X and a Y. So what's the probability that the first child will be a male? It is a 1 in 2 probability, and that is written as a fraction, by the way. That's how you write probability. It's a 1 in 2 chance. So probability that will be female, again, it is 1 in 2 because 2 of the squares are female, and there are 4 total squares with our answers in it. So these are the four squares that can be answer type squares. Okay, so those are our answers. Why is it possible to predict the sex of the offspring? We know it's a 1 in 2 because the male can only pass on an X or a Y. Only males pass on either or. All right. Now, diagramming sex lineage. So, the X chromosome carries a number of genes that have no corresponding allele on the Y. Again, the X is different than the Y. And that's why we treat the X as recessive. A colorblind man marries a woman who is homozygous for normal color vision. So we're going to put the male, we're going to put him here. He's going to be X and Y, and the female is going to be X and X. The question then is, what letters did they get? A colorblind man. So they gave you this as being lowercase n. So that's what we're going to use. We're going to stick with what they gave us. Now, again, you could just use an X with a lowercase c, and then a normal X could just be an X and nothing else on it. But we're going to go with what they gave us. All right, so remember, the Y chromosome doesn't get anything, and that's why males can't be carriers. Okay, we talked about this the other day, possibly that we can have females that are carriers, but males can't be carriers. Men can't mask this gene. They have whatever is on the X chromosome. The females can mask it. So a woman who's homozygous for normal vision, so she's going to have a capital N on each of these. So capital N, and where's my superscript at? There we go, capital N. All right, so summarize the results. So again, tell me in terms of males and females. So we are going to have, we're going to copy this, because this is what's getting transferred over there, and actually here as well. And we're going to copy this, and this. All right. Now, and then we copy this and drop this down. See how this one goes there, these ones go there. All right, so of the females, so let's just go with this. 100% normal females, 0% colorblind females. Now, there's an additional thing you can note with the females. 100% of normal females are carriers. All right, and that's important. Whereas males, notice that both males are normal. So 100% normal males and 0% color blind males. All right. A man with normal color vision, so this is the normal X chromosome, and marries a colorblind woman. So actually we need the colorblind allele there and there. So what do we have combined here? Now the reason I'm putting the male in there first, whereas up here I put the female, it's just because I want this capital N to be there first. So I know that these are females, and both females are the same, both female combinations, and that is normal and carriers. So 100% of the females are normal, and 0% are colorblind, but 100% of the female are carriers in this one as well. So we do have the same female results for this one. All right. Now, what about the males? Okay, so the males, we're going to have this. And remember, the Y chromosome doesn't carry anything, so the males just have whatever is there in their X chromosome. So they got this information, they got it from their mom, and since their mom's colorblind, they have to be colorblind. So similar but slightly different results. Okay. Now, the difference here is that 0% of the males are normal and 100% of the males are colorblind. They have no option but to be colorblind. All right. In humans, hemophilia is a disease for which blood fails to clot normally. So basically what they're doing here is they're going to use X capital H and X lowercase h. Understand X lowercase h, since it's a recessive disorder, is going to be hemophiliac female. So a man with normal clotting. All right, so we're going to have X with a capital H because he has normal clotting. Now, see, I would prefer to use the letter N here because normal is dominant. But again, they gave us these letters, so that's what we're going to use. Today, we're going to use just the X, and instead of a capital H, we're just going to use just an X. You don't even need that capital H there at all. And then we're going to use actually a subscript instead of a superscript for the lowercase h here. So a woman who's a carrier. So the woman has capital H here. And down here, for her second allele, she's going to have a lowercase h. So what do we have in this first box here? It's going to be X capital H, X capital H, because X capital H, X capital H. All right. Now, what are we going to have? Actually, we're going to need another one right here because this X capital H comes down. Here we have an X with a lowercase h, so we'll put that right there and right there. Now, these are our males. And there you go. We have 2 males, 2 females. So, what is the father's genotype? All right. Again, it's this X capital HY. Let me see if I can copy and paste that over there. Nope. Still no. All right. Anyways, here it is. Just put that there. And then the mothers, it's these 2. We'll see. Nah. Okay. Yeah, that just goes there. And then fill out this punnet. We did that. All right, what percentage of the boys will have hemophilia? This boy does not have hemophilia. This boy does. So what percentage of the boys will have hemophilia? 50%. What percentage of the girls will be carriers? So this female right here is completely normal. This one's normal but has the recessive trait, so 50% of the girls will be carriers. All right, what percentage of the boys will have normal clotting ability? This is a normal clotting boy, so that is 50%. What percentage of the girls will be normal? Well, 100% will be normal, but 50% will be carriers. Why do you think it's uncommon for girls to be affected by hemophilia? Because basically they need two recessive, two recessive copies of the trait. Whereas guys only need the one because they have the Y, and the Y doesn't carry any information. All right, so cross a white-eyed female. Okay, so here we go. In fruit flies, eye color is determined is sex-linked. Red eye color, capital R, is dominant over white color. Now, they're sex-linked, so you have to use X chromosomes. I see so many students not use X and Y chromosomes here because they see the capital R and lowercase r, so they assume it's just normal Mendelian genetics. But it says they are sex-linked, so use your superscripts, people. So it says cross a white-eyed female with a red-eyed male, so we know the male is going to have a capital R. The female is going to be white-eyed, so she's going to have stupid caps locks. All right, let's see here. I got to put a superscript. There we go. And there we go. All right. So I like how copying and pasting shows you that where I'm getting these letters from. All right, and that's how the grid kind of works. So, red-eyed females, 100%. White-eyed females, 0%. By the way, 100% of the females are also carriers. All right, red-eyed males, 0%. And white-eyed males, 100%. Remember, we divided out by males and females in terms of percentage. All right, let me see if I can just copy this whole graph. It might save me some time here. No. Ooh. All right, let's see here. Come on. Oh, well. We'll call this good enough. All right, so this is going to be a red-eyed female. Heterozygous red-eyed females. So we need to do this, which then changes this. And I got to change that to superscript. So this is actually not saving me any time at all. All right. And then, let's see. And a white-eyed male. So there, the rest of this is good. So the females are going to be, let's see, red-eyed. So 100% are red-eyed. Only 50% are carriers, though. White-eyed females, that's 0%. Red-eyed males, actually, I need to fix this right here. So this male is going to be red-eyed. All right, so 50% of the males are going to have red eyes, and the males are going, white-eyed males are going to be 50%. So red-eyed male right here, white-eyed male. Okay. Let's see here if I do this. All right. And I'll put that one down a little bit. All right, so for letter C here, give us a little more space. All right, so white-eyed female. So there we go, white-eyed female and a white-eyed male. All right, so here we go. And then this actually also looks correct. So red-eyed females are going to be 0. White-eyed females are going to be 100%. Red-eyed males are going to be 0%. And white-eyed males are going to be 100. All right, down here. Heterozygous red-eyed females with a red-eyed male. I'm going to copy this chart because it's most similar to this. Go down here. And all right, so heterozygous red-eyed female, red-eyed male. Oh, I just realized up here that this should have been a white-eyed male. So actually I already had these results because I goofed this up big time. And I'm not going to re-record this whole video because I'm almost done with the key. I am sorry about that. All right, so let's just have this. Okay, so look at here. This one I got to fix. Letter B I got to fix here. So red-eyed females are 50%. White-eyed females are going to be 50%. So red-eyed female, white-eyed female. Notice that this red-eyed female is also a carrier. Red-eyed males are 50%. White-eyed males are 50%. Letter C was correct. I did do that one correct. And now we have letter D. This is going to be a heterozygous red-eyed female, good, with a red-eyed male. That's good. So red-eyed females. So both of those are red-eyed. That's 100. White-eyed females are going to be 0%. Notice that 50% of the females will be carriers. Red-eyed males will be 50%, and white-eyed males are going to be 50%. Okay, go ahead and take a moment to check that. And then we will jump back in with the sex-linked traits. Okay, I am back. Okay, so if a trait is sex-linked recessive, then a male will have the disease if the X chromosome carries a trait. For example, color blindness is recessive. So looking at what we just did here, basically, let me get the pen here. All right, so basically we have a couple of options for males, right? You can have an X, and then we had capital N and Y for a normal male. And then you have a colorblind male. And that's X lowercase n with a Y, right? Now, I don't like actually doing it like this. And what we just saw here a bit ago was that you don't have to necessarily the homework we just did, yes, they did it this way, but one thing that you can do is just get rid of those n's there and just, okay, so what we're going to say then is that this is a normal male. And if it's a colorblind trait, we're just going to put a C on the X. That's it, okay? So this is a colorblind male. This is a normal male. Now, can men be carriers? We talked about this when we were going over the homework. No, men can't be carriers. So men really only have two options. Either they're this or they're this. So if we look at this pattern, we can see, all right, this is definitely a recessive trait. But when we start looking at it, we're like, well, look, only guys have the trait. This might be a sex-linked trait. Now, you do have to kind of just work it out, unfortunately. You can't just, we definitely know it's recessive because it skips generations. 2 parents that have it or don't have it and a child that does. So we do know that the shaded in ones are recessive. All right. But only men have it. If you're not sure on a test or a question and you see only guys that have it, just if you're guessing because you're having trouble working it out, it's sex-linked. All right. Even if it's most of the guys, there's a specific set of conditions to have a girl that has it, okay? So here we have, all right, a male that doesn't have it and a male that does have it. And always fill out the men first on these charts because the men are really easy to figure out because either they have it or they don't. And since you don't have carriers, again, it just makes it exponentially easier to figure out. So basically, if they're filled in, they're this one. And if they're not filled in, then they're this one, right? So here we have a male, all right, and he is colorblind. And here we have a male, and he is not colorblind, so we're just giving him this trait, okay? Now, again, going back to how we did this yesterday, this would have been X capital N, and this would have been X lowercase n. It's just a different way of doing that. Just remember, these are representations of what the genetic code is. All right, so fill in all the males because the males are exceptionally easy to fill in. They're either an X and a Y if they're blank, or they're an X with a C and a Y. Now, if we're doing this for hemophilia, again, it's the same thing. You can just put like a lowercase h. So again, male doesn't have it, so that's XY. Here's a male that does have it, so he's an X with a C and a Y. All right. Has it, so he's an X with a C and a Y. Doesn't have it, so just XY. All right, I'm not going to finish filling out the rest of the males. I think you got the point by now. Now, go back and fill in the females. For females, we have 3 options. Technically 4. So we know that they're going to be XX. And if they're completely normal, then we're just going to write XX. But yesterday, we would have wrote it X capital N, X capital N. They could be a carrier, which yesterday would have been X capital N, X lowercase n. We're going to write it like this, X and then X with a lowercase c. Or they're colorblind, X, C, X, C. All right, this is a colorblind female. Now, will this one be shaded? No. Will this one be shaded? No. Will this one be shaded? Yes. Do we have any shaded circles? Well, no. So there solves that problem. We aren't going to use this one at all down here. All right. As a matter of fact, you rarely are going to fill in something where it's a female. It's like this. Matter of fact, these two are going to be somewhat iffy at times. Because what if we just can't tell for certain? Well, you're going to have a lot of times where you have an X and then an X with a question mark. And I'm just moving this over here because I just don't want to write down onto my chart there. You know what? Actually, I am just going to put it down there because I don't want you guys to be confused there. So erase that. All right. And pen. All right. So there. We can also have this where we know she's normal, but what's the second trait? And you could put XX or XXC. Another way of doing it is writing X, and then the second one, we're just not sure if she's a carrier or not, so just put a little question mark there. All right, it's a little bit less writing that way. All right, so we know that there are no females that are filled in, so we're not going to put this option that's in the box. The question is, do we know she's normal, or do we know she's a carrier? And there's 2 ways to know that a female is a carrier. So right here, this female is normal, right? So the question is She's XX, and do we know for certain she's a carrier or not? Is there a way to tell, or is she going to be a question mark because she might be a carrier? Well, honestly, you can tell 100% for certain that she is a carrier. How do you know she's a carrier? All right, so let's just say she got this, well, let me click on the pen here. All right, so let's say this X chromosome, let's say it came from her mom. And so we have this mom here, and we don't know if she's a carrier because we have no other information about her other than her children. And she has a son, and he doesn't have it, so we don't know for certain if this mother doesn't have it. Now, she married into the family. She probably doesn't have the color blindness trait, but honestly, we're just not sure, so I'm going to put a little question mark there. So let's say this X chromosome came from mom. Well, there you go. That X came from there. So where did this X come from? Well, it had to come from dad, right? Dad has to give one of the X chromosomes to her. And since dad is colorblind, we know 100% for certain that this female is a carrier. There's no doubt about it. So if you have a girl who has a dad that has it, we know that she's a carrier. And that's actually pretty darn easy to fill out. Like, look around, and do you see any other females that have a father that has it? And actually, I'm not seeing any in this pedigree, okay? So that's one way of telling that a female's a carrier. The other one is, all right, so here we have a male, and he has it. So where did he get this X chromosome from? Could he have gotten it from his dad? Well, no, his dad's X chromosome is normal, first of all. Second of all, if he got an X chromosome from his dad, he wouldn't be a boy, he'd be a girl, and we'd have a circle there instead. And just, no, that doesn't work. The Y chromosome had to come from dad. So this Y had to be donated to each of his sons, right? So where did the X come from? Well, then the X had to come from mom. So there's two ways of telling if a female is a carrier for certain. Number one is look at dad. Does dad have it? Okay, then she's a carrier. The other way is look at the children. Does the son have it? If the son has it, then she has to be a carrier. All right, she has children that have it. And look, she has a normal son and two sons that have it. By the way, this is not her son. This one right here is not her son. This is somebody who married into the family. If this was her son, this would be some incest going on there. No, that's not happening, okay? So are there any other females we can tell are carriers? So this female right here, she could be a carrier. And here's how I figured out she could be a carrier. You have to bear with me. Let's go back here. All right, so this woman right here, could she be a carrier? She could be. Matter of fact, we know she is. But if we go back to her mom, she could have got a normal X from dad and a recessive X from her mom. And so therefore she could be a carrier. But furthermore, what else did I tell you to look at? Either if her dad has it, well, her dad doesn't, but she could have got it from her mom in terms of the carrier. But also look at her son. She has a son that has it. Since she has a son that has it, we know she's a carrier. So we know this is 100% for correct. All right. We know she's a carrier. All right. Now, could have this girl got a normal X from dad? Possible. Could have she got a normal X from mom? Yes. So she could be this, or she could be XXC because she could have got a normal X from dad and a recessive X from mom. And so she could be a carrier, but we don't know for certain until she has some children. And probably a couple of boys, although honestly, just one boy comes along that's colorblind and we already know she's a carrier. If she has 5 or 6 boys that are not colorblind, we can be pretty confident that she's not a carrier. All right, so again, does dad have it? No. Does the son have it? Yes, a son has it, so we know she's a carrier. And basically what you're going to find is either we know she's a carrier or we're just not sure if she's a carrier. And that's really what happens with a lot of these sex-linked pedigrees with the women, okay? So anyways, you can finish working this out. I'm not going to go through the whole thing. As a matter of fact, your exercise today is doing this, except for instead of using C's, you're going to be using H's because we're going to do hemophilia. All right? We already did the Punnett squares for these. So look at this. Is this a dominant or a recessive trait? And if you look, you see a female and a male that don't have it, and they produce children that do. So we know it's recessive. Is it autosomal or sex-linked? Well, you see mostly guys have it, but do all the guys have it? Or only guys have it? No, we got a couple females. So the question you've got to ask yourself is this possible? And really the key here is tracing it back to the females. Like, for example, this male could have come from a carrier, male could have came from a carrier, male could have came from a carrier, male could have came from a carrier. And that doesn't really necessarily help you much. And you can fill this whole thing out. But really, if it's sex-linked, if there's some females that have it, that's where you need to focus. So let's say this was hemophilia, right? Then we know these two girls would be this. These girls, since dad has it, we know would be lowercase h, by the way. I'm hoping that some of you already have figured this out, whether this is sex-linked or not sex-linked. All right. If we start over here, is this possible? Well, if mom is a carrier here, she could give a recessive trait to this daughter, and we know that dad would have it. Right? And so if this X and this X were combined, then we could indeed end up with this female right there. All right? The only way a female can get it, though, is if dad has it and mom is a carrier. Remember, dads cannot be carriers in sex-linked traits, which then brings us over to this side. Dads can't be carriers, right? So this dad is just normal XY. And even if mom is a carrier, this is not possible because this recessive trait came from mom. This recessive trait came from dad. So we know that no, this is not sex-linked. This is autosomal. Now, actually, on the next slide, notice I actually fixed it there. So the only female that has it has a dad that has it and a mother that's a carrier. Okay, that makes sense. All right. So this is dominant recessive. Again, it's recessive. The only change is I got rid of the female that was the carrier. So this definitely is possible now. So we do know that this is probably sex-linked because we have only males that have it other than this one female. And the female has a dad that has it and a mom who could be a carrier. So this would be dad. He has hemophilia. And this is mom. She could be a carrier. So this means that this woman here would be X lowercase h and X lowercase h. Now, again, we know that men that don't have it are XY. The men are easy. Always fill out the men first, okay? Then look at the females to figure out if it's sex-linked or not, generally speaking. So this male's not shaded in, so we know he's an XY. Or do we? He's not shaded in because it's asking you the question, right? Where does Y chromosome come from? Dad. Where'd the X chromosome come from? Mom. So actually, we do know that this guy would have to be XH. He would have to be, he'd have to have it. And so therefore, this would have to be shaded in. This male's the same scenario. He had to get his X from mom. Remember, men always get the sex-linked traits from mom because they got the Y chromosome from dad. So this would have to be shaded in. All right. Do we know what these females are? Well, since we know that there's a normal X there, we know that both of these females are going to be carriers because mom had it. And so therefore, they have to have a normal X from dad and the recessive X from mom. Okay? So yes, we do know that this one is a recessive trait, skips generations, and we know that this one is sex-linked because only the men have it except for one female, and the one female that has it has a dad that has it and a mom that's a carrier. Make sense? I hope so. Anyways, you're going to practice this more today. Primarily looking at hemophilia with the one royal family. And so what we're going to do here is, let's take a look at this real quick. And so if you read this background information, notice that right here it says, below each person on the pedigree, list the possible or probable genotypes. So you're going to figure it out. Again, fill in the males first. The males are either X8, lowercase h with a Y. That's all the blank ones. I'm sorry, all the filled in ones is an X with a lowercase with a h with a Y. Or a normal male. So either they're hemophiliac males, X lowercase hy, or they're normal males, just XY. And then the females, you want to look, does she have a son that has it? Yes, she has to be a carrier. Does she have a father that has it? Yes, she has to be a carrier. All right. Now, some of them you're not going to know. All right. We know that this person right here, number 2, is a carrier because she has a son that has it, right? So she's a carrier. I mean, some of the daughters could be carriers, but we're not certain because, like, for example, this girl didn't produce any children, so we don't know if she's a carrier or not. So that's where you can put the XX question mark. It's either that or right, XX or XXH. All right, answer the questions. Again, notice up here it says below each person in the pedigree, write their genotypes. Then down here, just going to talk about some circumstances. What are the possible genotypes of children of a woman whose father was a hemophiliac? So just, you have to kind of think about what's going on here, okay? A woman whose father was a hemophiliac, what does that make her? Again, women who have a father that had it are carriers. So she has to be a carrier, and whose husband's normal. So he's got a normal genotype. All right, fill in the genotypes here. Now, students get confused with this, but all you're doing here is you're kind of just running some hypotheticals. So let me just grab one here. What is the chance of number 1 getting hemophilia from his father? So here's number 1. And so number 1 married number 2. And so what would be the chances of him getting hemophilia from his father? So let me go to a place where I can draw. So here's number 1, and he's married to number 2. And so what's the chance of him getting hemophilia from his father? So we're going to just add this here. All right, this really isn't there. Actually, here, let me... I didn't want to erase the whole thing. Oh, well. I'll rewrite it. No, go back. Okay, there we go. So pen, there we go. Of number 1, married to number 2. Okay, so here, I'll just draw a dashed line so you can see, again, what if? We know that he was born from parents. At least we think so. All right, so we're going to have a hypothetical square here. So what's his chance of getting this from his father? So here's the father. Ooh, this is going to be a rough circle. There. We're just going to just draw a circle there for mom. Okay. So there's his grandmother, right? Do men ever get it from their father? Oh, if the father had it, let's say, whatever trait it is, say it's hemophilia we're looking at, could have he got that from his dad? No, he got a Y from his dad. So he would only get whatever his mom had. And the only way he can get it from his mom is if she's a carrier or has it. So could he get it from, what's the percent chance of number 1 getting it from his father? Well, none. 0. There's no chance because men can't get the trait from their father. All right. So anyways, that is this upcoming homework assignment. I kind of wanted to give you some details about there just because those are some points that some students have difficulty with. Okay? All right. Thank you very much and have a great day.